Hello and welcome to another screencast episode of Three Devs and a Maybe. My name's Ed Mann, and today we are again joined by Joe Watkins. How you doing, Joe?
I'm good. Hi, everyone.
Hopefully you would have already watched the previous one, which is our kind of beginner language constructs episode, where we discussed like the nitty-gritty kind of each of the individual files, the locations of things. And we made up a simple hipster for keyword function. Well, it wasn't a function, sorry, it was a keyword language construct. And it essentially was like an identity function for strings. So if the expression returned a string, it would allow it and just pass it through, else it would complain and throw an exception. And that really kind of highlighted each of the individual bits, like the lexer, the parser, the AST, down to the compile stage. So what we then thought was maybe go into a bit more detail on, well, not really more detail, but more kind of more use cases where you're most likely going to be using these things. You're not going to be making a hipster function. You're going to be doing, interesting additions to the language. And, over the weekend, well, one thing Joe, you said was, Ed, ping me some ideas if you have any. I was like, okay, yeah, I'll try and think of some stuff. And like over Twitter, I'm just sending you these like ideas thinking, well, it may be quite cool if you could like do this. And then essentially all you do is just send me the actual patch for it. So it's been really enjoyable just actually seeing all this kind of work. And I mean, I've been able to kind of look more into the source. So I think the more we have these different kind of extensions, we'll go into the nitty gritty of each one of them, but like using different looping structures and things like that, using if conditional blocks and all these things. So yeah, what I suppose what the best thing to do is to start off with one of them and then go through each individually. And I think the best one, I guess, the first one that I actually started off thinking about was the looping one. And I'm just wondering, maybe we could start with that and see how that goes.
Yeah.
Are you on that, Bright? So yeah, so Joe's been nice enough to kind of get out each individual patch is in its own branch, and we'll put it in the show notes for each one of them. So I said to Joe, I was like, well, it'd be quite cool if you just had this loop keyword that is like a while true. Because, while true is quite ambiguous. I mean, it makes sense as a programmer, but it's not very, declarative of what's actually going on. Essentially, I just want to loop. So it'd be quite fun to have this idea of you have loop and then you provide it in an expression block and it will just loop through until, within that block you break out. So, yeah, let's see kind of how this goes through. So we start off, obviously, with the lexer.
Yes, we do. So we start off with the lexer.
And we need to tokenize it, don't we? Yeah, so we're going to get the lexer loop token.
So yeah, the first thing to do is tokenize the loop keyword.
So pretty much that's identical to what we had to do with the hipster one. So we provide the lexer with the idea that, look, by the way, if you ever get this loop keyword, this loop, string token string, this loop string, put this into a token or tokenize it as loop.
Yeah, so that's all there is to do in the lexer. And then we open up the parser again, and
the parser hit. This is because the actual string on the right. That's just a pretty printed kind of thing for it. Yeah,
that's just for humans.
And this is where the magic actually happens. Then.
Yeah, this is where you create your abstract syntax. So we've got a new statement, t loop, and then that's the token we defined in the lexer, and then statement, which is a rule defined here. It's the rule that we're in now. So that allows you to, recursively embedded syntax. So yeah, that's all there is there. And then there's...
Because once we've got this, so now we've tokenized it, now we need to pass it to the AST, the abstract syntax tree, because new in PHP 7 is PHP now has an AST. That allows us to do optimizations and things like that eventually on. But then what happens then is it will go to the compiler. So, yep. So the AST
primarily at the moment, the AST just allows us to split the stage that was what used to be one stage, parsing and compiling. So as the file was parsed, literally as the characters were parsed, it would be compiled. So now. It's two stages where, as it's passed, the abstract syntax tree is created, and then that's used to create the actual compiled code.
And I suppose that helps kind of split out the problems, because they are two separate problems, aren't they, really, what you're trying to do?
And like the structures you need have got different requirements and things like that, so it was quite awkward before, and now it's quite tidy. But no, we're not using the ability to run optimizations on AST yet. I mean, it might come, but not yet.
It's just it's definitely an advantage. I mean, well, actually, your experience with PHP 5, like, how much do you prefer the code base now? Like, do you like the splitting up? Do you find it a lot more easier and readable and more manageable?
Well, PHP 5 was with us for a long time, And that gave us all a long time to get to know it. And I don't know PHP 7 as well. And at the moment, I still find it quite a lot more difficult to do. Like
understanding of yeah.
It's not necessarily the understanding. It's just everything that was simple before is now considerably more complicated, and not many people know this information. Obviously, it's written in code, but you don't always see it when the code's in front of you. You need someone to point out this is how it works now, and it just hasn't really lived long enough for there to be like a large pool of expertise to draw on. So that makes it slow when you come to really complicated stuff. But it is nicer. I mean, it is nicer because there's like APIs for stuff now, and before it was you basically manually built everything yourself, and you had to copy strings and literal strings and things like that, and it was just really complicated. And with the other improvements that came with Zend, it makes writing patches nicer, but just a bit more difficult at the moment. But I mean, ask me again in 5 years when I've had this.
That's exactly yeah. So you'll eventually be like, well, I love PHP 7 now, and you probably won't even remember the PHP 5 stuff.
Honestly, I can't remember how to use PHP 5. I can't remember how to debug it, or like internally, when people come and report bugs with PHP 5 stuff, I'm just like, well, that's dead to me.
Well, it has to be. I mean, this is a whole new kind of code base. I mean, essentially, a lot of it has been rewritten because of all these additions.
Yeah.
So it's a new learning curve, and so we've got the Lexa all set up now, and the Lexa's given us a token that's been tokenized, and then what we need to do is now the parser needs to come along and make it into an abstract syntax tree.
Yeah.
And what we've got is you've got the other file there, which is the Zend.ast header file. So we have to define in there this is a one child node. So you can see there with the comments, it's quite nice that they've just, they split them out into that. And it allows, say, that one child, which is in our case is the statement itself. And at the end, we're just going to put in RAST loop constant.
Yeah, that's all you do in there. That's like I said last time, that's all you have to do in there. But you should work on exporting your new AST, but we're not going to do that again because it's boring.
So what's interesting to actually notice there is you've got like the headers. Sorry for that. Stepping between files here. Like you've got like the U's and stuff at the top there. So that though actually are they zero child nodes? Where? You've got like the Zend.ast.
These are lists.
Those are lists. Right. Interesting.
It's more magic.
Right.
These are lists.
So you have different types, and a node can be considered a whole separate expression that needs to be evaluated in its own right, I guess. Like it goes recursively down that you have to.
Well, it can be an expression or a statement, or like it says, a list or a declaration. That's the nature of abstract syntax. It's abstract.
Yep.
So we can say we've got a node, but we don't have to say anything more about it. It's an abstract node that represents a yield from or an unpack or whatever. And then its child nodes are the expression or further statements or operands or whatever. And it's abstract, so you don't have to say any more about it than that.
Because it will deal with it when it needs to come to it.
But yeah, when it actually when it needs to be compiled, that's when it needs to mean. That's when it needs to mean. So when you have to turn it into operands or specific opcodes or a certain pattern or something like that. So yeah, at the moment it's just abstract. So all we need to describe it in very loose kind of terms, and that's what all we need to do here.
Brilliant. So yes, we've got the header file set up now, and then we go into the actual implementation of this. I'm guessing, though, we actually
the compile function. So
here we go. So this is really this is where the actual work happens of actually creating.
Yeah, at the moment we've just got abstract syntax. It doesn't do anything. Now, this is where the code is compiled. It seems a bit magical, but if you think about how a jump works, how a loop works, it's basically execute this code, then jump back to the top, execute this code, jump back to the top.
As long as it meets that condition, keep doing it, and it's like a go-to. I shouldn't really say that, but it is kind of like, go back up to here and keep doing it.
So what we've got to do first is establish where is the top. So before we do anything, you can see here, we get in our statements, which is the only child in the abstract syntax tree. And then what we do first is get the next op number, which is the next stop line, the next instruction to be executed.
And that can be considered the beginning of this loop. Yeah.
Yeah. And then you instruct Zen to emit opcodes for a loop. But since we're not actually going to use the loop, we can emit an op, and then opcache will optimize that away.
Okay, so this is a no op for it. So how does that kind of work then? We have to initialize the loop. But
we have to initialize the loop because that's the tidiest way to get the compiler to know that we're beginning you could try and do it with labels and jumps and go-tos, but this is the simplest way.
Okay.
The tidiest way to do it. So you begin the loop, and then that emits the next instruction that we're going to jump to, and then after the loop, and then you compile the statements. So all the code for the statements inside the loop are compiled.
So a nice thing like this with the language construct is you don't care about the other statements, do you? We're not caring about that. We just essentially say,
syntax, so you can just you've got a function somewhere that can handle it. So that is nice actually. This is what I mean. Before this here now is quite rare. This what I've highlighted here. This is what I meant by like manually doing stuff, like getting addresses and.
So what does that actually do then, like on a high layman's terms, kind of?
What the stuff that's highlighted now?
Yeah, stuff that's highlighted looks pointers.
What that is it's emitted. We'll have a quick look. What are we looking at? It's for each. So for each is basically the same. I mean, it's a loop, but at the beginning of the loop, rather than doing nothing of executing the first instruction, you move forward to the next.
You're then setting up these variables within that
Yeah. So all of that, it emits the opcodes for the loop, and then after the loop, after it's done all that, it goes back and it has to fetch the op line that was reset. And then the one, so it goes reset, then fetch, then execute your codes, then reset, fetch, execute your code. So, and then it fetches backwards the reset op line and tells it to jump to the next op code. And then it ends the loop. So you don't get much of that now though.
We're quite lucky now.
Yeah, you can jump around and do looping and emit jumps and manipulate them with API functions, which is much nicer. So yeah, that's where we were. You compile your statements, and then all the opcodes are emitted for the statements in your loop, and then you emit the jump back to the beginning of the loop, and then you end the loop.
Brilliant. Okay, so from here now we've got a compiled. So it's essentially the abstract syntax tree is compilable to the Zend virtual machine.
This is obviously added to the function that compiles statements. This is a
big switch statement that just does all the hard work.
Yeah, because we've added a new statement. We go into the switch and add the caller for the new kind that we've created, which I just had there. There it is.
Yeah, there we go.
Yeah. So that's how that works. And then I think that's it for this one. This is just like syntax sugar. So there's no like virtual machine stuff. This is what people refer to as when they say, "Oh, that's just sugar." That's what they mean. It doesn't actually add any features. It's like another way of writing.
So it's just a cleaner way of writing something, because essentially, as what you're doing there is what maybe, I suppose, if you're doing a while true loop, would kind of be emitted to the virtual machine anyway. You know, I don't know whether the optimizations would happen. It would be very. I don't know what would
be different. It would be different. But that you don't need it for stuff that's just sugar. You don't need to touch the VM. You just need those changes. So all of these things that we're looking at today are on my GitHub.
Definitely put that in the show notes. It's a really interesting branch. I'm looking through it. Sorry, repo, because I've been looking through all the branches and stuff you post on there. You just, the ideas and things.
So that's that, and we just see that. We see that run.
Yeah, definitely. Let's see how it works. So this is making. So you've got a development build. Well, not a development build, but your own build from source of PHP 7 with these changes in now. Compiling that so you can actually run the CGI, from the command line.
CLI.
Yeah, CLI. Sorry. Yep. Right, here we go. Yeah, let's make a base case, or else we'll infinite loop time. There you go.
Mm.
Very nice. That's awesome.
So it's that easy. The easiest ones are, but the most useful as well are the ones that people refer to as syntax sugar, because you don't really want to be going in to the virtual machine and adding new stuff.
No, absolutely not. I mean, the base concepts are there already. You might as well take advantage of them.
Yeah, that's all you're trying to do is make the things that people already do easier. Introducing brand new stuff that's foreign to people, that gets a lot of resistance, and for good reason. I mean, when you go and start changing all the VM handlers and stuff, I mean, that
gets scary.
Yeah.
Yeah. Things can break easily then, and in changes like that can be, kind of, and again, essentially, you're kind of making a change that needs to be managed and handled, for years to come. So it's a very expensive decision.
Yeah, you've got to think about the future for a long time, and obviously when things get of a certain complexity, there's the bus factor to think of.
Yep, absolutely.
Well. So yeah, that's the loop.
Brilliant. So we've got the loop one now. So and then I just don't know what do you feel is the next one, good one to go on to, kind of a progression.
We had.
Look at the branches. Here we go.
Unless
was a good one, yeah. So when you're in Ruby world, you'll see the unless. And essentially, what it is the negation. So it's an if not, this condition, do this. And, it reads quite well in some cases, because you can be like, unless I'm logged in, do this. So I said to, I was like to Joe, well, maybe something like that. And I'm guessing, is it quite similar in like its structure to how the loop worked? Like, with that, you haven't had to touch any of the VM or anything like that.
Well, you have to forgive me for saying that I don't remember, because I've written...
That's fine. Well, there we go. Let's open this up and see. So
yeah. So yeah, we've got our Lexus change again.
Lex up. So we've added that keyword in, and we're tokenizing that again. So we've done that bit.
And then we've got the token in there, and then our rule.
Here we go. Yep.
So this time I decided to introduce a new rule. Now, a thing to mention here is, I think the original idea, you had it the other way round.
Yeah, I kind of, because looking at what Ruby does is, is it allows you to do the condition after the fact. So you could do this if this, or do that unless that. And it can get quite scary looking, a bit messy.
Yeah, because a block, as in curly braces, is allowed on its own, and because T unless EXPR looks like a function call, there would be no way to disambiguate between a valid block and a call to a function called unless. So you have to think about conflicting.
Well, yeah, stuff that's already there. This is the kind of environment you're in. You've got to work within that means. And to be honest, actually, I think the way you implemented it actually looks nice. To be honest, because when I was writing these,
people expect,
yeah, that's it. It was very foreign the way that because I know you mentioned that you'd have to do this statement unless.
Yeah, to disambiguate it. Yeah. The thing is, when you try and introduce stuff and it's too ambiguous and it can't resolve it, it will tell you it can't resolve it, and it will tell you how many rules it can't resolve even, or how many conflicts there are.
And is that with Bison? Bison will do that for you.
Yeah.
Oh, nice.
So that is a thing to think about, conflicting syntax.
And so you made a brand new kind of constraint on this, like statement for this. And then this is essentially just doing the same thing as what we were doing with our loop, which is it's just getting the expression and the statement. And then based on the positioning, because it's positioned based on the zero, the number one, I'm guessing, number one is the actual, for us, is the token. Then we have to take into consideration the character. And then it will generate the...
Yeah, that's 3, that's 4, and statement is 5.
That will get some people where they think, why is, it's not based on placeholders, it's based on positioning of the whole statement.
It's actually quite nice, because in your head, have you ever started counting from 0?
That is a very good point. Yeah, no, you want to count from 1, you're told from a very young age, 1.
Yeah, so no one ever counts from 0, that would be really weird. But yeah, you get used to it, and it's only in here. I mean, you can't use that. It's not a valid variable name. It's a horrid variable name. I think you could actually use it, but it's horrible. So I know you can't.
So we've got that. So we've got the unless. We've made that. So now we just need the AST compilation.
The kind.
Oh yeah, absolutely. Sorry, yeah, you've got to include that.
Yeah, it's got two child nodes this time. The expression and the statement. So put it in the two child nodes group at the end there, and then we've got our.
This is the magic bit.
Yeah. Now here's our expression and statements, child 0 and 1.
So that's extracting those out and giving us the pointers to those, the expression and the statement that we can then use.
Yeah, the AST for those. And this is a node for a conditional jump.
Okay.
And this is the op line we're going to jump to.
So we have to, because obviously we have to meet that condition first before we even think about jumping into this. Else we need to just forget about it.
Yeah. We test negatively on the condition, NZ. There's lots of jump functions that do various things, so you don't have to write out it. You don't have to do it you don't have to do the same thing manually, if you know what I mean.
So it's good to go into the LXR and seeing what's all available.
Zen vmdef.h and just search Zen jump, and it'll come up with all the different matches for the different kinds of jumping it does. So this is quite simple. First, in this time, we compile the expression because that's required to test in the conditional jump. So we emit a conditional jump. That's the opcode. That's the condition, and I'm not sure what that is because I've forgotten. So we'll have a look.
Yep, let's have a look. I mean, it should be noted that throughout all of these screencasts, going back to the LXR is a really valuable tool. It's a great way of being able to know and quickly find information about the source. This
is the target, but we're going to update that in a minute after the statements are compiled.
Okay.
So we put 0 there, but if you know where you're going to jump to when you're emitting the jump, you can do it there. So then we compile the statements and emit those, and then we update the jump target so that it knows where to jump to. And then obviously we've added a new.
Add it to the big switch.
Yeah. In there.
Yeah, there we go.
It'll be in Zen compile stmt. There. That's all that's required for that.
And then there's no VM changes or anything, is there, that needs to be done? This is, again, some syntax sugar over what's already really available.
Yeah, we can have a look at the patch and the diff there. So we've got our AST changes, our compiler changes, parser changes, and that's...
There we go.
And then Alexa, and then that's it, yeah. So that's that. So we can make that and test that.
Yeah, let's see this unless in action.
Yeah. So,
so we make an example file.
So if you imagine where you might use this, I mean, it's horrible, and you can't.
It is very, very weird, isn't it?
It's nothing you can't do with different syntax, but I mean, if you try to just stretch yourself and imagine where you might use it, you might say, if you imagine inside a constructor or something, or inside an object, you might have a connected variable, and then you might do that, and then connect, but we're just going to put true.
Yep, we're just going to do so. Yeah, you do a side effect on it to see, and I mean, it's like things like if unless they're logged in, do this. I mean, it is just if not, if they're not logged in, do that.
Yeah. So that's
there we go.
That's that. Yeah.
That's awesome. Yeah, that's a great another kind of syntax sugar addition.
Yeah.
And then we've got, what else did we get? Yeah, so then there was another. I mean, I don't know which one do you want to touch upon next, which is kind of progressing up in complexity.
Probably the foreguard one.
Yep.
I mean, it's the response I got for writing this was not good. None of these are examples of things that you should RFC tomorrow. They're all just.
In fact, it's probably good that we're documenting these as not RFCable, because maybe people will think, "Oh, we could add this." It's like, well, probably don't.
Yeah, probably don't. Hitting on something that you should do is pretty rare. But the things you shouldn't do are how you get practice.
I think that's exactly it. Like, you have to learn by doing these things, because it is, as you say, very hard to find something that needs to be done. Like, a lot of what's already there. A lot of what you think, oh no, it's already doable. So it's nice to have these example cases, contrived examples that highlight these areas.
Now this time we don't change the Lexar because we haven't got any new tokens to Lex. Now. This time we'll have a look at what it's going to look like before we actually do it. Now the idea was that you would have you would put a guard here. Say, well, it's smaller than.
Yeah, something like that. So you're only going to get.
So that's how it's going to work. So it will break out of the loop when the condition's not met anymore. As you can see, that is extremely horrible, but it shows you about this because you can't have it without this strangeness here, because a for each doesn't have to have a block.
That's it. It doesn't need a block, doesn't.
Yeah, so the while underneath it, that doesn't have to have a block either. So you've got to think about disambiguating the syntax, and one way to do it is introducing weird tokens like this. You will have such a difficult time convincing anyone that it's a good idea to introduce new tokens, because stuff that looks weird, and people don't think about, well, it only looks weird because it's the first time I'm looking at it. In a year, it won't look weird. But people don't think about that, and you have to get past that initial factor.
Yep.
And it is a prohibitive thing. So let's look at the first. We look at the parser changes, because that's where it all starts in this one. Now, because we've added a new statement. Actually, in the last one we had
that. That was it. The unless included this.
Yeah, the unless included this. When you add new rules, you've got to say what the rule's going to return. So what that symbol's going to be, the double dollar symbol's going to be.
Yep.
Most of the time it will be typed, but also it could be a number here, see, or a string, which is a Zen string. So that's one thing you've got to do when you're adding new rules, which the last one did have. And obviously it's got token up there. Oh no, we've not got any new tokens here, have we? So it's just the new rules.
Just the new rule.
Yeah. So now this was the standard rule, and all we've done is stick our for guard in there. And we'll have a look at the rule in a minute. Well, you know what kind of abomination it is anyway. So we've had to stick the rule in, and also additionally pass it. So
we've had to update what the for does, obviously, and the for each.
We changed how many children it's got now.
Yep.
The AST reflects that, which we'll look at in a minute. We'll look. So we look at AST4 before we reload it. You see there, it's under 4 child nodes.
Yep.
And now
There you go. You've had to add.
But I terribly have not updated.
Naughty.
Yeah, I'm obviously a terrible person. But yeah, so
well, this is going in for an RSC, so you've got to clean this up.
Yeah, right. No. You've got to try and keep everything tidy. I didn't. Anyway, so yeah, we've updated the AST to say it's got more children, and we've passed the create function the additional child, and also we've added it to for each. So that's T4 and for each. So it works for both of the structures there. So we just have a look at the abominable rule. Okay, so it can either be empty, which means it's not required because you don't want to break everything.
Yep.
And in which case we just set the return value to null there. And then we pass out this awful thing that looks like a HTML markup. So yeah, we've got t while and then our expression, and we're creating a new AST kind, AST for guard, which has got one child, and we'll find it up here in the one child group in the AST header.
Yep.
Okay, so then what we've got to do now is change the compiler function so that it understands
this lovely AST.
The new for guard AST, yeah. Yeah, so here we've got the compiler for the for guard. So
yep.
Again, we compile our expression first because we're going to use it for the conditional jump, and then after we've done all the state, this is the only bit we've added here. Look, we have a look in, that's the only bit we've added in this function.
Because it's just essentially just adding on, tacking on this stuff that we want to make sure we guard it on each iteration.
And then after all this stuff here, we just check for guard AST again and update the jump target again like we did last time.
Yep.
So yeah, that's all that's required for that. And then the same kind of logic is also in compile for each. Where is it? There. So,
there we go. Yep, if for guard AST.
So exactly the same thing, and then update the jump target. So that's all the changes for there. That's all of it, isn't it?
Yeah, I think that is. I think that's going in for an RFC in about 5 minutes. Yeah, we're going to.
Yeah.
Yeah. So now we're just going to compile it and see how it works in practice.
Yeah. So
there you go. Yeah. So following on for the one we had, which was the guard for look, as long as you're less than 3, we're going to let you carry on. Else we're going to break out.
Yeah. So that's that. And I think the last branch we had was the with branch.
Ah, yes, absolutely. Yeah, this was one of the ones that you kind of you experimented with when you first played around with these language constructs.
Yeah, and what I first wanted to do was introduce you to all the different bits of like the virtual machine and all the different files. And this one didn't touch all of them, so we kind of.
It turned out to be easier than even the hipster one with the amount of things you actually had to.
Yeah. So
how does the with one work then? Is it all right to go through maybe an example of what you would use with first, and then we'll go into?
Oh yeah. Well,
is that cool?
Yep. Yep. Now, I'll just
reload all the files. That's cool. Here we go. Let's see how this will work.
So say you've got an object.
Using that new nice anonymous anonymous classes.
Yeah. So now in here, what we can do is call methods. We could also set variables. And that's it. And it's just a shortcut for having to type out this.
Constantly type in object, arrow, object, arrow.
So where it looks to me like it could be quite nice is actually in constructors, because I hate constructors that are just endless this, and it's so annoying. It's jarring to read, it's time wasting to type, and the margin for errors increase, and I wish there was an easier way, and this seems nicer than typing it all out. Other people have said, oh, well, what we could have was so that's a shortcut.
Right.
It's only really applicable to that one case, and I mean, I like it, but it only applies to that one thing. Whereas, what about when you're in the global scope? It's just as annoying having to type out the name of an object over and over again. But anyway, this is also widely hated. And, I didn't get a very good response for writing this.
But a great example, though, to add to the list of kind of understanding.
So that's what we're doing.
If you say that you need to play around with things like this to kind of get a feel to get something great, because you need to understand how these things work and what's possible.
And it's just a case of getting to know how the compiler works now and how the AST works now, and all you've got to do is try. It's not super complicated. It's mostly written in the code. And I mean, when it gets a bit more in detail and you're changing how the engine works, that's more difficult. But most stuff isn't that. We're just trying to make programming easier. And you can totally ignore all the people that say, oh, why are you focusing on sugar rather than new features? Well, because nobody wants new features, and
that's exactly it, yeah.
Because they haven't really considered what new features cost. When you try to do anything of complexity, it has an impact beyond what you can see, and you've got to acknowledge that about anything complicated, and try and keep it simple. The language is quite mature now, and it's got most of the stuff it's going to kind of get in terms of groundbreaking features. The task now is just to make it easier, I think. This is our with. So
we've got the with stream again, and then it's going to tokenize that.
Yep, we got the new with token, and then we've got, I can't remember how I did it this time. Right, so there's our with token.
Yep.
And human readable string, and they're not. Oh yes. Okay, so here's,
because this has got a couple of bits, hasn't it? Because it's got the idea of a list that you can supply and things like that, so it's going to be a bit more advanced.
Yeah, it's a bit more. It's a bit more involved. There's more than one kind of AST you introduce, and you've got to kind of introduce a new structure. But like I said in the first one, the thing to do is imagine what the AST will look like, and that's quite simple. I mean, you want a node that's called with, which is there, and you want it to have an expression which is there, and you want it to have abbreviated statements. So you need to create a new kind of list, which is, if we have a look in, you create a new kind of list for the list of abbreviated statements.
Yep.
So if we look where it is in the AST kind, enumerated AST kind structure, we can see we've added it in this part now, which we haven't used in any of the others. So we've added it to the list nodes there.
So from here, then we've got this AST. We need,
and this rule here, the with statement list. This is really common. You find it in quite a lot of rules with the comma and then another list. So it says basically you can either have a with statement list, which is this rule itself, and a comma and another statement. So it's saying it's recursive. You can have it's kind of recursive.
Yep.
And then or you can just have one statement on its own without a comma. So if it's just the one statement on its own, that's where you create the list. So
it makes it cleaner. It doesn't mean you don't have to have the trailing comma then, I'm guessing.
You don't have to have the trailing comma, yeah. And then the with statement rule, which is here. And remember, these are all defined as AST at the top there.
Oh, yep, up at the top, yeah, well, we've got our...
up at the top, there. The with statement and with statement list and with, they're all new rules that return AST, so we done that up there first. Okay, so then now we've got, this is the abbreviated kind of statements that we support.
Yeah, so that's the assignment you've got, and then also you say you've got the property name argument list, which is called.
Yeah, this is short for a function call. This rule is defined already and used elsewhere for the same purpose, and so is this. So you just create a call with your method name and the argument list, or if it's matches this rule, it's an assignment to a property. And you could probably do other ones, but I couldn't think of any that were useful, really. So yeah, then we've got another different kind of AST with our name and our expression. And again, it's not two because this counts as a token.
Yep.
So now we've got the compiler function for this, which is
so is this going to be a little bit more advanced?
It's really difficult to type 1W. Yeah.
Here we go. Wow. Okay.
So first we've got the object, which is the expression, and the statement abstract syntax. So we get the statement list from the statement abstract syntax first. We're going to loop through the children in the list and switch on the kind, and we've got our two different enumerated kinds. This one first, and then the assign one.
Yep.
Now, all of this stuff here is basically constructed from the same logic inside the compiler. So there's no like API function, but you have to kind of do a bit of manual labour, which is normally going to be the case for complicated stuff. We've got the methods and args, and if we, I think that's probably from, if you look at where this is emitted elsewhere in the file, this is all based on that.
Yep.
So what it's saying is, emit ops is saying let's return opcode op1 op2. So we're not going to use a return because we don't care about it. Initialize the method on the object, and then we set. Now, this where you would just expect to have the method node in there because it's op2. But if it's a constant string, we cache them, and the emit opcode doesn't do that for you. So you have to do that.
So this is an optimization then, is it?
Basically, and it's what's expected as well in this already defined opcode. So we set it as constant. We add the literal and a cache slot. We allocate a cache slot, and if it's not constant, like it's a variable or something else, then we just set the node, which is what the emit op does, basically.
Okay.
And then we compile the call, and that's it for the call one. And then again, this is constructed from the assign object logic. So we compile the required expressions, the object, the value, and the property, and we emit the opcode, and then we cache the constant for the property, or set the node. And then the emit op data is because you can only have op1 and op2.
Okay.
And we've used them all. See, we've got...
right, yeah.
We've used them all. So op data is like a cheat to allow you to have like another operand. So you can set it next. So that's what that is. And I'll just put panic there.
Yeah, because if you don't get anything else, we don't know what to do with you.
We don't know what to do with it, but I didn't go into like how to handle that. So that's all we needed for there. So that's our compiler function, AST changes, parser changes, and scanner changes. That's it for that one too.
So let's see this in action.
Yeah. Let's do it with thing.
It's interesting. It's an int and strings okay as being them, but array.
Yeah, it's weird, isn't it?
That's interesting.
So yeah, that's weird.
There you go. You can see it all. You can see how it works. That's great, Joe. That's awesome. Yeah, being able to see like kind of the progression up from, the simplest we kind of had, which was the loop construct, which only really syntactic sugar, along with the unless, which is syntactic sugar, and then the for guard again really was syntactic sugar. But this kind of has a bit more to it, a bit more weight behind it.
Yeah.
Brilliant. I'm thinking that's pretty much it. Actually, that's quite a good I think place to stop.
Cool.
Awesome. All right then, audience. Well, it's been really interesting, like another screencast, kind of going into this, and it'd be great to hopefully get Joe on again. We can kind of again go through different bits and bobs, and leave comments in the box below at YouTube, and also send us to us and tweet maybe Joe, if I'm sure he doesn't mind, and get feedback from it. It'd be really good to know what kind of you feel, what you want to learn about, and what kind of is interest of you to you. I think this has given a really good understanding overview of kind of what needs the places you need to look into and stuff. And awesome. All right then, audience. Well, we'll speak to you next week. Goodbye.